Okay. I see that speaker maybe is here. So we can start. And today our speaker is Nikolai Vovchanskii with the talk about random measures which arise in the Arratia flow. Okay, let's start.
Koля, we cannot hear you probably.
Koля?
Can you hear me now?
Yes.
Yes.
Yeah, good. It's a bit tricky in Linux Mint sometimes working with Zoom. So I start sharing my screen. Good. I will keep my video right now on, but if we experience some problems or inconveniences with internet connection, I will turn it off. So please let me know if something is wrong. Today's talk is a joint work with Professor Girsanov. So I will use we not only as it should be due to some mathematical standards of speaking, but also for this reason. And we're discussing so-called endpoint measures, densities, that we use to describe the point process that is associated with an Arratia flow. And in some sense, this talk is a continuation of the talk or the presentation of Girsanov. However, on introducing the very first concepts that are similar to those used in the talk of Girsanov, we will move in another direction because the main goal of this talk is to provide a way to describe the connection between the point densities that arise in the case of the Arratia flows with drift and the densities that arise when addressing the Arratia flow with no drift or with zero drift. So let me start with such notation. We will consider the Arratia flow on a finite time interval. So this is an Arratia flow with drift A, that is every trajectory, sorry, okay, solves a stochastic differential equation for where Vu is a standard linear process with respect to the filtration generated by the flow, and the quadratic characteristic of this linear process is just t minus theta uv plus, well, theta uv is the first moment, particles starting from u and v correspondingly meet. I will always assume throughout the whole talk that A is Lipschitz continuous and bounded. In case where A is just 0, I will drop this superscript in xa and will write just x. Let me introduce some notation. If we are given a point from Rn by xau, possibly with just dot, we will denote a random vector consisting of all trajectories starting from all coordinates of u, and by this Gaussic t of u, I will denote the set of values of coordinates of this vector at time t. For the size of this set, I will use vertical bars. So this is, for instance, is less than n. So our main references for today. This is tribe, Vovchanskii plus their co-authors. Also the paper of Fomichov in communicational stochastic analysis, and results of Dorogobtsev. Go. See, something is wrong with this. Yeah, now it's correct. So let me start with the first definition. So suppose that we are given n, we are given some k that is less than n, and some point u belonging to delta n, where delta n throughout the whole paper is a first simplex, the set of all points in Rn that satisfy this inequality. Then the nk point density Pa and k at time t of u is a measurable function, and I will always assume that all functions we consider are measurable. So I will not write measurable every time it is needed. It is supposed to hold this condition of measurability. A function on Rk such that it always holds whatever the function f small from a k to r k to r is, that the mathematical expectation of the sum where all these are distinct f of v from 1 to k, so this is just v1 vk, indicator that we have not less than k points, otherwise it doesn't have any sense. dy. And if we replace in this definition this set with just the set of all values at time t, and the condition that there should be greater than that, and if this condition is corrected in an appropriate way, we can define the k point density. So this object is heavily reminiscent of those studied by Tribe and Vovchanskii.
Koля, let me ask you, as far as I remember, they studied the case when A equal to 0.
Yes, of
Am
course.
I right?
Yes, of course.
Yes. So they proved the existence of the density in that case. But in a general case, we also have to check that these densities exist.
Yes, and we will do this, but before doing this, we will introduce some additional density, and we'll prove first the existence of that density, and then we will derive the existence of these nk point densities from the existence of the former ones.
Okay. Koля, may I also ask a question?
Yes.
Could you show us slide a little bit above? Here. So here is indicator. So greater than k or equal k. Greater than or equal or
greater than or equal. So this just means that this expression makes sense. Since they are distinct, if they are less than points, we cannot just write
these are first k numbers.
We take all possible k tuples from this set.
Okay, I see.
All possible.
Ola, I have also a question. The assumption that a drift coefficient is Lipschitz, it is needed for the existence of the Arratia flow, or it is needed for some results about the endpoint densities?
First of all, it is needed for the existence of the flow and for the existence of the specific exponentials that are used in the Girsanov Arratia flows.
Okay, we don't know that the Arratia flow exists if coefficient is not Lipschitz.
Generally speaking, if the function that is integrated in those integrals that are used in the definition of those exponentials may not exist if the function is not Lipschitz.
Okay. Thank you.
So generally speaking, yes, we need some, maybe boundness for some results that we discussed can be dropped. That is true, but not the Lipschitz continuity. So to describe, to work with such densities, we want to introduce a so-called coalescence scheme. So suppose we have n-dimensional is a process with continuous trajectories. With continuous trajectories. Oh, sorry. I did something wrong, right?
Yes.
You stopped the demonstration.
I stopped the demonstration. I also closed the window with most X journal. Now we are back. And share screen and here. Now we should be back to normal. To the normal situation. Continuous trajectories with coalescence, which means that if two coordinates for some s, they stay equal on the rest of them. Also, additionally, and this is going to hold for all processes we are going to discuss, I suppose that tau ek, which is infinity of such numbers, satisfies following property that all tau k such that they are less than t are distinct. Now suppose that the number of points that survived to the time t capital is exactly n minus kappa. Then, by means of the following recurrent scheme, we can define, firstly, G1, which is the minimal number such that there exists another number, that psi I of tau 1.
I do not understand, you said that all theta are distinct, or you consider theta which are distinct?
We suppose additionally that this holds.
But it could not happen. Let's assume that the second trajectory first coalesce and then this pair coalesce with the third trajectory. Then tau 1, 3 and tau 2, 3 should be the same, right?
Yeah. Of course. Yeah. So
we can have maximum n minus 1 stopping times, right?
Yeah, so what I wanted to say is that only pairwise collisions possible. Thank you very much. Is this correction possible? No triple collisions. And tau 1 and tau n minus kappa are just all collision times that are less than t, but ordered in ascending order. So this is the moment of the first collision, tau 2 is the moment of the second collision, and so on. Then we can define C1, this is psi without the J1's coordinate. Now we can define J2 as a minimum number such that there exists J Now we can get a vector, a random process of the lesser dimension, and so on. So let me just draw a picture, which is going to be simple. So this is tau 1, this is tau 2, this is tau 3. Suppose that we have 1, 2, 3, 4, and J1 is 3. J2, since we eliminated this and reordered, renumbered them in mu, this is 2, and J3 is going to be 1.
Koля, I'm sorry again, but probably you order in another way, right? You start from the smallest one, like 1.
Well, essentially, I didn't fix any ordering of psi, except that we have psi 1 and psi n, so the usual ordering. So it doesn't matter as soon as we just remove this and mechanically. So if in this vector some coordinate disappears and we just shift the numbering one position left to the left. But of course, what follows we will consider in some, but not, we will consider ordered processes with ordered coordinates, but not always, actually. So, we will have a collection of numbers And we call this a coalescence scheme for Xi.
Nikolai, can I ask you the following question? It seems that when we have just finite number of trajectories of process which coalesce after the meeting, from topological point of view, we have some random forest from
Yes.
the finite number of trees.
Yes.
Can we just say that every collision scheme is related to different topological type of the forest?
It depends, what do you mean by topology? I mean, suppose that you have such tree, these two trees, are they the same or they are different?
They are different.
Very different. Then yes, you are right, we can speak about trees, we can speak about partitions, as it was originally proposed by you actually in one of your papers. But right now it's a redundant information, I'd say.
So we just
need these numbers.
The order of collisions.
Yeah, we just know which pair of processes meet firstly.
Okay, and do some notation for this.
Yeah, for this purpose solely. So we do not use anything. We consider this as Xi as just elements of the such set. So the empty set corresponds to the case where no collisions happen, and S, H, and K is the number of all such cut tuples that J, Y belongs. Let me be careful with this. And E from 1 to K. So this means K collisions between N trajectories. And trajectories. But now we can define for the Arratia flow for point UN for coalescence scheme and for some J that is greater than K, we can define the N minus J point density that corresponds to this start point, to this coalescence scheme, and to to the N minus G, which is the number of surviving particles. This is A, N, S, N minus G at time t from U. So this is a measurable function on Rn minus J such exactly this coalescence scheme is observed. And this should be equal. And in terms of these new densities, we will discuss the densities of the previous types. So, before speaking about the existence of such densities, let me make a brief review of the Girsanov theorem. For Arratia flows. So this is results of Vovchanskii and Vovchanskii. So suppose that we are given a sequence such that just u1 un such that the set of all their's coordinate is dense in the closed interval from 0 to 1. Then T1 is equal to T capital, tau 1. Tau k is equal to the moment when the particle starting from uk meets any particle starting from a point with a smaller number. K is greater than 2. Now define un as the sum from k to 1 tau k ukt dx. This is a standard integral, so this is a linear process. So this is a Lebesgue integral understood pathwise. And now we can define Tn of un of a very standard structure, and there exists L2 limits of En.
Kola, may I ask you also a short question about the integrals that you wrote, the first one? Okay, you wrote with respect to up to the finite index, but of course you can write that to the infinity. Is that the same as you will write the double integral with respect to u, but divided by the length of cluster?
So this is integral from 1 to 0, integral from 1 to tau of u, dx ut in notation of Dorogotsov.
Mm-hmm.
I just
I'm asking whether that integral can be written as the usual double integral, one integral with respect to the process x as a martingale with respect to t, and after that you integrate with respect to u, but then you need to compensate the length of cluster, just divide by the length of cluster. It seems that it is so. Okay, that question just to pay your attention that it could.
Think I cannot answer. Maybe I do not understand fully.
Yes, Vitaly, we have a different form, but it is not necessary now.
Yes,
Moreover,
of course.
moreover, now those different forms will be much more difficult to discuss.
Mm-hmm. I need to think about it. So there are limits of these integrals, and they do not depend on u. And then it is known that the distribution of xa is absolutely continuous with respect to the distribution of x in the scalar space of the random elements with values in the space of continuous functions on the interval from 0 to t, and density is exactly of this form. And of course, as corollary, if you have a finite number of trajectories, they're absolutely continuous in the product space with density And here just U for U belonging to Rn, because you can define this integral for any U. In the definition, we use only trajectory starting from this, the first n coordinate. I will formulate also one technical lemma that we will need further, that the mathematical expectation of if m is greater or equal than n, so the proof is standard, so I will omit it. And now we are ready to work with the existence of densities. So, next lemma, P, A, N, S, G, T exists if these parameters are consistent in the sense that G, N, and S are related in an obvious way. So J is less than N minus K, where S belongs to this set. To prove, let us consider Vg belonging to the set of values at time t only distinct. Here we have some subset of the first simplex. It doesn't matter, but let us suppose. Here we have S, X, A of U, the coalescence scheme of this coalescing finite-dimensional process. And now applying the Girsanov theorem, we can drop A here. Here we have 1 from 1 to G. Here we have the coalescence scheme of just and I can rewrite this as follows. This is LG. This is the set, so all elements are automatically distinct. LE belongs from 1 to K, K from 1 to G. Now, mathematical expectation, indicator of A has UT. And here I will introduce the notation that if I have L, a set of indexes, and have some vector from Rn, I will write z to the power L and z to the power minus L for the vector that contains only coordinates from L, and this contains all coordinates of the initial vector except for those in L. Here I have the conditional expectation with respect to this vector. But since L is fixed, x, u, t, L is killed upon exiting delta G, if we suppose additionally that all I are ordered, Brownian motion. So this expression is less than the sum over all those L integrals over A where G T is the density of Brownian motion killed upon exiting the first simplex. Delta G. So it is sufficient to conclude that this measure, which is defined by this expression, is absolutely continuous with respect to the Lebesgue measure. Now I want to speak about some representation in the case when we have no drift. So suppose this is our first simplex. Let us denote the portions of the boundary of this first simplex as follows. Mj, this is of course the union of all set J is strictly less than all the boundary, but it all that matters for us. And then we can establish the following theorem. For any S such that S equals to this collection of natural numbers, and for any start point almost everywhere, this density has a representation given via the following integral. So we have n minus chi integrals with respect to the time variables. Now we have integrals on the boundaries of the shrinking of the same sequence of shrinking simplexes and here comes the integrand 1 u z1 d mu z2 g n minus 1 t2 minus t1 s n j1 Z1, Z2 times 3 dots P n minus k plus 1 T n minus k minus T n minus k minus 1 plus 2 J n minus k minus 1 say n minus k minus 1. And the last expression is just the density of the killed on exiting the simplex Brownian motion. Here, R is the surface measure. D mu, that is the outward normal derivative with respect to z variables, and S mg is a mapping from this portion of the boundary to the whole simplex, and it just removes the j plus 1 coordinate. And this is exactly the second in a pair of two equal coordinates, the second one. Because here we have j and j plus 1 coordinates equal, we just remove the one that is equal to the first one.
I have a question. May I ask?
Yes, of course.
You formulate the statement for almost all U, as I understand, right?
Yes.
But, cannot you conclude any type of continuity of the endpoint density with respect to parameter U, or some kind of regularity?
Yes, actually we can conclude that this holds for all Y.
And you think that you have continuity, say, at least?
Yeah, we'll discuss it. Well, first of all, this is a continuous function. And so this is just an iterative application of the formula for the solution for the corresponding Cauchy problem. So we start with endpoints, we find the first collision, we live on the proper surface, portion of the surface, and so on, until we get to the case where only k points survived, and then we just move to our final point k.
Okay.
So the proof is simple in the sense you just need to apply this formula again and again, and it's continuous, of course. If k, j in this formula doesn't equal n minus k, you can also, using the same idea as in the proof of the existence result, use some representations, but since they're repetitive, I will omit them. Now we have the representation of something for P, A, 0, and S, K. So we can relate this density for the densities that we initially introduced and that didn't use this coalescence scheme via the following lemma, which is a corollary of the formula of total probability, essentially. And we have that P, sorry, shifted my yeah, here, and K for any A, Next learn about the approximation and the relation, the approximation of PAKT with no n. So where we consider all points for all particles instead of a finite dimensional family of them. And for that, suppose that we have something like this. We have a sequence of points in Rn such that the first point is always 0, this last one is always 1, I will denote this by delta n. Then, firstly, PA for any k t is almost everywhere limit t. Secondly, sometimes it is possible to find the speed of convergence. So for instance, exists an absolute constant such a similar result can be obtained in case where here we have higher dimensions.
Excuse me, Koля, in the last line, maybe the difference is estimated, yeah?
Yeah, the difference, of course. Let me show very quickly the proof of the last result, because the first result is just application of the classical limit theorems. So here, after some additional arguments, which I will skip, if A epsilon is this small set, we can consider the limit, the upper limit So essentially, this means that if you have a very small epsilon, there is very small probability that two or more points will hit this set. So you can pass from the indicators that you have points to the indicators that you have exactly one point. And now, doing the same trick as, for instance, in the talk of Gliniane, where she used dual Brownian web or dual Arratia flow, we can say that this is related to the cases. Here are our points from un. Here is x plus epsilon. And what we want in this expression, we want that no points from the coordinates, starting from the coordinates of un, hit the set. This means that there should be trajectories of the dual flow starting from x and x by epsilon. They will hit inside in between of two subsequent coordinates of un. So we can say that this is less than the probability that for dual flow we do not have a meeting for this point, but this interval is inside of some interval of this type. And this is less than the indicator that we have 2 points that are on the distance less than delta n, and here stands p 0 to no collision happening, t x plus epsilon to y1 y2 dy1 dy2. Now this is just the density of the Wiener process with scaling, and this is to t1 minus this simple expression. So using this and passing to the limit, we can conclude. And if we consider initially not pi1 and not p1 and p1 here, but p2, for instance, we can use very same reasoning, but here we will get something of higher dimensions. And if we use a representation in terms of those iterated integrals over simplexes, we can conclude that such estimate, or even better estimate, can be obtained for higher dimensions here. The problem, I don't know how to write it other than just by hands. It's very tedious in the sense that you need to use the Taylor expansion and to retain the integrability of your estimates when you go from one integral to another. So there should be a way to write it down in a more neat way. And now we are ready. We have very little time, but I will try. We need to speak about Brownian bridges before speaking about the relation between the finite dimensional densities for Arratia flow with drift and the Arratia flow with no drift. So why do we need to speak about Brownian bridges? Suppose that we have a standard Brownian motion in Rn. Then we can, if some u is fixed, we can define a process with coalescence by means of the following scheme. So we start that the first coordinate coincides with the first coordinates of W1. Theta k is the infimum of those t.
Do you mean W1 plus U1?
No. So I always work with this process and with this process, just for notational reasons. Thank you for the question. It's actually important. Here. And then so we just kill the trajectory with higher number as soon as it hits a trajectory with lower number, with a lower number. K minus 1. As soon as the hitting appears, the meeting happens. And of course, the distribution of the Arratia flow coincides with the distribution of this process that we built, and those stochastic exponentials that we considered, they have exactly the same distribution as their simpler counterparts, that is, exponents of such type. dwkt minus the second part, which just the ordinary integrals is a squared and 1 over 2 before the sum. So, since we are interested in our finite dimensional densities, and the definition of those densities contains only the condition for the points of the flow to hit specific neighborhoods of some points at time t capital, which is fixed, we can consider the distribution of this exponential at least conditional on this. So essentially, this is heavily reminiscent of the idea Vitaly Konerovsky told us last time. Why? Because we will decompose the trajectory of a linear process as a value at the last moment of time and the Brownian bridge. And Brownian bridge is independent of Wk of t. I recall that Brownian bridge admits the following two representations. First of all, it solves the stochastic differential equations. Stochastic differential equation dt when t is less than t capital, it equals 0 at the beginning and at the end of the interval, and also is a centered, it is a centered Gaussian process with covariance function s minus t minus multiplied by the fraction. The numerator is t minus s maximum t, and here just t capital. So now if I introduce the moments that the coordinates of our initial simple Brownian motions meet, and introduced for a given y from Rn the similar constructions, but for the process of this type. The curve T equals T. Then first of all, we can see that no triple collisions are possible for this process, for this collection, and no triple collisions are possible for this collection also, because it's a centered Gaussian process, so it meets a representation term. It meets a good representation, and it can be shown. I will skip that part. And they're closely related in the sense that this holds on assured. Now, given some coalescence scheme, we can find random numbers lambda eg of S, where E ranges from 1 to 0 and J from 1 to N, such that on the set, for instance, if we additionally put, this is just always T capital, because it may be so that two specific coordinates do not meet at all. And of course, essentially, these numbers do not depend on the realization of the W. Now we can define the following function. And beta is the unit process with respect to the filtration generated by our Brown and bridge. So it reminds us of the stochastic exponential, but it is different, since here stands some additional terms. Some additional terms stands. Actually, two of them. Now, the result, which shows why we needed all this construction, is that the conditional mathematical expectation of this construction can be expressed in terms of this exponential. So I want to just give the idea of the proof. And the idea of the proof is that, firstly, we should notice that on this set, our initial A is the functions just coincide with such functions. So we approximate integrals plus us dw kt with progressively measurable but much simpler functions such that amk tys is the sum over g from 1 to m minus 1 indicator jt m j plus 1 tm of t, and here starts a very standard construction in the theory of stochastic integration. R y s dr. And now this integral can be recalculated in the sense as dt plus
Koля, I'm sorry, and what is W and what is WK? So could you please...
W is a standard Brownian motion. WK is just the case coordinate of this W.
But what about measurability? You consider stochastic integral, is it anticipative?
Right now, everything is progressively measurable.
No, I mean, you have W T capital.
Yes.
And so this is the terminal time.
Yes, but all coordinates of W are, how to say, independent.
And WK is case coordinate of W.
Yes.
I see. Mm-hmm.
So it's like we fix all coordinates except for the case ones, and then we write this integral. Because tau k depends also on other coordinates.
I mean, this function AK of T, W of T, it is not FT measurable.
It is measurable with with respect to the sigma alpha generated by the case coordinate if you fix all trajectories except for k. Okay. In this sense.
Thank you.
You are welcome. And this is AK R Y y at k. And now here we can apply the SDE representation for Brownian bridge and obtain the interpretation in terms of integral with d beta and the integral with respect to the drift. And then since I am out of time, we can show that since this is essentially the same, we can use the disintegration theorem in this expression to calculate a conditional expectation with respect to the values of W at time t. And if we do everything properly, correctly, we will have exactly this representation. Now I want to formulate the following lemma, that for any coalescence scheme, this indicator is almost surely continuous whenever ym converges to y, when m approaches infinity. Should I explain why it is so, or can I skip it?
Just say the idea because the time.
Okay, so the idea is as follows. We need to consider all possible pairs, and the collision happens when the difference hits this line, which is just a straight line with different angles. And if we change y, we change the angle. And if a collision happened for y, the limit one, we can say that here should hold something or reminiscent of the iterated logarithm law, since every Brownian bridge can be rewritten as some linear process on different scale. And it can be shown that when ym is close enough to y, this line will still hit this curves, which means that we are going to have the collision happening even if ym is not equal to y, but it should be close to y.
Okay, it's enough.
So this is geometric explanation. And now we can formulate two main results in some sense of this section. So theorem one of this section is that if we have, so the corollary, an important corollary is that this conditional expectation is continuous function. It's a very good function. It also we can also have estimates on this conditional expectation, implying that it's integrable with respect to any Gaussian measure. So it's any power of this random variable is less than C1, C2 to the power C1 times the exponential to the power times exponent to the power C2 times the norm of y. Now, if we have and then for all y, we have two representations. The first one, sum over all subsets of size G here is just a standard Gaussian density with no killing. I will write then I will explain notation. Here, P of S is the set of the indexes of the particles that have survived. Up to moment t. And if I have something like this just means that firstly I take only coordinates from the vector k, and then I either exclude coordinates from L when we have a minus, or take only coordinates from L when we have minus. So we take all possible subsets of size G because we're interested in what happens to exactly this number of coordinates. This factor corresponds to this, and then we integrate with respect to all other coordinates. This is the coordinates that have survived but do not participate in a subset L, and this is the coordinates that died. And this is the what is left after the application of the Girsanov theorem for the Arratia flow and the application of the previous result, where we replace the stochastic exponential used in the Girsanov theorem by a simpler stochastic exponential in terms of Brownian bridges. And I think that I will just formulate the last result. Now, suppose that the elements of this set has its elements ordered in ascending order. And again, if we have some set of indexes, now they are not bounded from above, we can define a random vector as the vector constituted of the points from this set x of t if there are enough points to select. So if the number of points that have survived is greater than the maximum index used, or just some symmetry state otherwise. This is the symmetry. Then we have a subprobabilistic density, which is the distribution of XL and this is rho L T U. So this is the distribution of this random vector, and we can write again the sum over all subsets. Now there is no restriction of LK. They can be arbitrary. Here stands and here stands the conditional expectation of the corresponding exponential conditional on this event. You can have the analog of the last result when you replace x tu with just the set of all values and redefine this set, this random vector appropriately. Then you will lose here n, you will lose here u, but you will have the same expression in the sense that p a k t o y is equal to the sum over this very same sets rho L T, which is not going to depend on u anymore, and here we extend the conditional expectation of the whole exponential. So the exponential calculated with respect to the dense subset of starting points. I think I am out of time, right?
Yeah.
Yeah. Thank you for your attention and sorry for taking more time than it was supposed to take.
Okay, thank you for the presentation. And maybe somebody have questions or comments, please. If there are no questions, let me make some comments about the subject of this talk. As it is known, this k-point densities for Arratia flow without drift can be expressed in algebraic way using some analog of determinant Vovchanskii, where in the coordinates we have some tails of standard Gaussian distribution. And this expression are more or less complicated in the case when we have no drift. So during doing this job, we were inspired by the idea that maybe we cannot have such a good expression for k-point densities for Arratia flow with drift, but using Girsanov's theorem we can have representation, and then this work is not finished yet, and then using estimation on the conditional expectation of the Girsanov exponent, we can get the estimation for endpoint densities for Arratia flow with drift. It was the main basic idea when we began the job. It occurs that we need a lot of technical moments, so we did it here using approach with disintegration, Brownian bridge, etc. But our main aim is to estimate precisely the endpoint densities for Arratia flow with drifts. As we can see, it can help when we study, for example, limit theorems for integrals from functionals with respect to Arratia flow, as it was done in the talk of Katerina Glimina. This is what I wanted to say about the subject of the talk. Okay, if there are no other questions, I have a small announcement that for my private reason, we have a 2-week break. And after this, our seminar will start again and continue up to the new year. Everybody will get the email with the announcement. Thank you for attention and bye for today.
Goodbye.
Goodbye.
Bye.
Goodbye.
Goodbye.
Goodbye.